Hello everyone. So today's subject is gravity, one of these fundamental forces of nature that I talked about in the first lecture. And it's this very weak force, attractive force between all things that have mass. So these two objects actually have a very weak attractive force between them. But the place where we really notice it is the attractive force of this object by the Earth. The Earth attracts that, and so it pulls it down when I let it go. And my weight, the weight of this is the Earth's attractive force on it. My weight is the Earth's attractive force on me. So the objects like this or me, relatively small objects, are held together by the EM force, the force between adjacent atoms. So the electrons of one atom are attracted to the protons of a neighboring atom. That's what holds this thing together. So, and it holds it together pretty good. This is a fairly strong substance. Big objects like the Earth can't be held together that way. They're too big to be held together by forces between adjacent atoms. They are held together by gravity. So here's a photograph of the Earth. Not only are we held to the Earth by gravity, the whole Earth is held together by gravity. All this giant mass of the Earth is held together by gravity. And the atmosphere of the Earth is held to the Earth by gravity. You can't really see the atmosphere on this figure, but there's about a 60-mile deep sea of air that's held to the Earth. That's why we have the air here. That's held to Earth by gravity. So on the scale of planets, gravity is the dominant force, the one that is most noticeable, the one that dominates the physical dynamics of things. So the Earth is held together by gravity. The Earth is attracted toward the Sun, orbits the Sun because of the attractive force of gravity by the Sun. Gravity was discovered, it was the first of the four fundamental forces to be discovered, even though it's the weakest. It was first discovered in the 1600s. And one of the people involved in the discovery is this person. This is Johannes Kepler. He was an astronomer, and in the early part of the 1600s, he was able to use astronomical observations of the orbits, of the movement of the planets through the sky, to find out the true shapes of the orbits of the planets. And here's a modern picture of the orbits of some of the objects around the Sun. You can see the orbit of Jupiter, the orbit of Mars, the orbit of Earth, Venus, Mercury, and so forth. This right here is the orbit of a comet. He found out that the orbits of all the objects that orbit the Sun have a shape called an ellipse, and he found out that the speed that they move in their orbits is a function of where they are on that elliptical path. An ellipse is just like an oval shape. It's not really important what the shape is like, but he discovered, first of all, that the planets orbit the Sun and not the other way around, but that they move in this elliptical shape. And he came up with 3 laws of planetary motion. One that says shapes of the orbits of the planets are elliptical, another that related how fast the planet goes as a function of where it is in this elliptical orbit, and the third that relates the size of the orbit to the amount of time it takes to go around once. Those are now called Newton's 3 laws of planetary motion. And they were an amazing discovery because, well, partly because he was able to prove that the Sun is at the center of the solar system being orbited by the planets. People thought that the Earth was at the center before that. He was able to prove by plotting these shapes that it was the Sun that was at the center. But later on in the 1600s, this is Isaac Newton. He was born in 1642, I think. He knew of Kepler's laws of motion because they came before him, and he said, you know what, all these laws would be true if there's an invisible attractive force between the Sun and the planets, and it has a particular mathematical form. In other words, the force is described by a particular mathematical equation. And it was this equation. So where m sub 1 is the mass of the Sun, m sub 2 is the mass of a planet, d is the distance between the Sun and that planet. If there's this is true, it would give rise to all of Kepler's laws of planetary motion. Newton was a mathematical genius, and so he was able to infer this mathematical law just by noting what Kepler said, which Kepler didn't have an explanation for why the planets moved in elliptical orbits. But here's an explanation, because there's this invisible attractive force between things that have mass. And he also extended this and he said, maybe this is a universal law of gravity. In other words, all objects that have mass attract all other objects that have mass. Not only does the sun attract the planets and the earth attract the moon, but all objects that have mass attract all other objects that have mass. So the reason this drops when I let it go is because the earth's mass attracts the mass of this, and it does so with this same equation. So in this figure down here I have a chicken and an apple, and they're separated by distance d. Now a chicken's mass is pretty small, a couple of kilograms, and an apple's mass is also quite small. When you put the chicken's mass in for m sub 1, the apple's mass for m sub 2, this turns out to be a very, very small force. And that is why we don't notice, the attractive force between small objects, because it's just very, very weak. G is called the gravitational constant. When you put that number in along with these other numbers, it tells you the force. G is a very, very small number, which for objects that have small masses makes the attractive force a very, very small number. So that's why we don't normally notice the gravitational force between things, except for the Earth's gravitational attractive force on ourselves and other objects on the surface of the Earth. So nobody was able to measure the gravitational attractive force between small objects for about 100 years after Isaac Newton. The first time it was done was by a guy named Cavendish. I think he was French. And what he did was he didn't use chickens and apples. He had these gray balls, or lead balls, pretty massive lead balls. And then there was a kind of a barbell suspended on a wire. Those red lead balls are sort of close to the gray lead balls. And in his experiment, they started out at these locations, and then he turned the wire so that the red balls got closer to the big gray balls, so that there would be a gravitational attractive force of the gray balls on the red ones. And because the red balls were closer to the gray balls, the attractive force got greater, and it actually twisted the wire a tiny bit. So it doesn't take much force to twist a wire a little bit. So he devised, this is his way that he devised, Cavendish devised, to measure an extremely small gravitational attractive force between these things. And he measured this force. And of course today we have much more sophisticated instruments to do this sort of experiment. It turned out that Cavendish's answer, his measurement of the force, was correct to within about 1.1%. So he did this accurate, even back in the 1770s, he did this this experiment quite well. It's a very difficult experiment because the attractive force between those even heavy lead balls is really, really small. So from that he was able to derive the constant, the gravitational constant, which nobody knew before that. So they couldn't make real calculations of the gravitational force. This is the modern calculation of the force, or modern measurement of a force, which has been done more accurately than Cavendish did it 200 years ago. And let me just use this now to calculate the gravitational attractive force between a chicken and an apple to show you that it really is a very weak force. So now the chicken's mass, I'm saying, is about 2 kilograms. That's probably a typical chicken. And I'm saying the apple's mass is 1 kilogram. That would actually be a really heavy apple. Let's say it's a pumpkin. So a 2 kilogram chicken and a 1 kilogram pumpkin are separated by 2 meters distance. So I now have all the numbers. I can put the gravitational constant in for G, and 2 kilograms is m sub 1, 1 kilogram is m sub 2, D is 2 meters, the distance between them. And here I've put the numbers in. I didn't include the units just because I didn't want to confuse the issue here. So here's the gravitational constant times 2 times 1 over 2 squared, and when you calculate that, you get 3.34 times 10 to the minus 11 newtons. That 10 to the minus 11, that's a really small number, right? That's 1 over 100 billion. It's a really tiny number. So 3.34 times 10 to the minus 11 is a real small number. In pounds, the newton is the standard international unit of force, named after Isaac Newton, because he discovered gravity. But the pound is a more familiar unit of force. When you hold a 1 pound object in your hand, the force against your hand from that object is 1 pound. So that's a unit of force. And so translating from newtons to pounds, you divide by 4.448, and it turns out it's 7.5 times 10 to the minus 12 pounds. 7.5 trillionths of a pound. So that's a really tiny force, right? That is why you don't normally notice the gravitational attractive force between chickens and apples, because it's really tiny. I mean, even large objects like 2 cars next to each other in a parking lot, if you calculate that force, it's way too small, probably way too small to measure. So it's a very weak force. And so let me do another calculation. This time that'll turn out a much stronger force, and that is my weight. So here's the Earth and me. That little dot on there. Of course, I'm not actually that big with respect to the Earth, so I'm not shown to scale with the Earth here. But you get the idea. So let's put in my own mass, the mass of the Earth, the gravitational constant, and the distance between our centers of mass. The center of mass of the Earth is the radius of the Earth. It's a round object, right? The radius of the Earth is 6,378,100 meters. That's the distance I put in for d. Now you might say, well, aren't I attracted to all bits of the Earth simultaneously? In other words, I'm attracted to this bit and to this bit and to this and this and this and this and this. You could add up these millions of bits. You could do it that way to find my weight. But it turns out because Earth is spherically symmetric, all you got to do is you can assume all the mass of the Earth is at the center. And if I put in the radius of the Earth, the distance from me to the center of mass of the Earth, and I put in the Earth's mass, it'll give you the correct answer. So when I do this, I put in the numbers. So I did include the units this time, but don't bother too much with the units. Okay, here's the mass of the Earth, 5.98 times 10 to the 24 kilograms. 5.98 trillion kilograms. The Earth is enormous, right? It's this very, very heavy object. So it is a big mass. And here's my mass, about 65 kilograms. Here's the radius of the Earth, and that gets squared. And when you calculate this, now you get 638 newtons. So whereas before the attractive force between a chicken and an apple was a tiny fraction of a newton, here's a very measurable force. So this is the force that I can feel, that my legs feel the Earth attracting me with. And this is about 144 pounds. So that's my weight. So your weight is the Earth's gravitational attractive force on you. Now, you might say, well, isn't mass and weight really the same thing? They're not quite the same thing. Mass is an intrinsic property. It's a measure of the amount of stuff that's in my body. If I went to the moon, I'd have the same mass because my body wouldn't change, right? But my weight would be lower because the moon's gravitational attractive force is smaller on a thing on its surface because the moon's mass is smaller. So you'd put in a smaller mass for the attracting body. So weight is the attractive force of the gravitational object that you're standing on, whereas mass is an intrinsic property. There's a little bit of a difference between mass and weight. So you're going to do a couple of these calculations, including this same one, the gravitational attractive force of the Earth on a 65 kilogram person. But you're also going to calculate the gravitational attractive force between 2 million kilogram buildings that are 50 meters apart. And you'll see, even in that case, it's a pretty small attractive force. Now I just want to say one more thing about gravity. it was discovered around the beginning of the 20th century, the beginning of the 1900s, that Newton's law of gravity is not quite exactly right. It's almost exactly right for most things you got to use it for, but it's not exactly right. Some things your calculations on the gravitational attractive force become wrong, and we now know of objects out there in the universe where Newton's law doesn't work very well at all, because there's a more accurate theory of gravity that was discovered by this guy, Albert Einstein, around 1915, and it's called general relativity. You won't have to deal with that in the gravity exercise. Later on, I'll come back to it when I talk about some other subjects, because it actually tells us some things about the universe that we would not have known if it were not for the discovery of this more accurate theory of gravity. But just to, since this is a discussion on gravity, I wanted to talk a little bit about general relativity. Okay, so there's a little bit about the gravitational force. That should get you going on the exercise.